What's up, everybody? We are moving on from what we were calling reciprocal functions now in section 5.3 to what we're going to call rational functions. The reciprocal functions that we've been studying were really just a special type of rational function, and so one of the goals in this video is going to be for you to know what a rational function is and so forth, but these are the more specific goals. I have two of them for this video. You're going to sketch and analyze the graph of a rational function that's in the form y equals k over x minus b. Now I hope that looks a lot like y equals k over x to you, because it really is just that same thing, but with a horizontal translation thrown in by an amount of b units to the left or to the right. And then the second goal is going to be to sketch and analyze the graph of a rational function that's in the form y equals ax plus b over cx plus d. Now I hope you recognize y equals a over ax plus b as kind of being just slope-intercept form. That's the equation of a line divided by the equation of a line, correct? So that's the second thing that we're going to be sketching and analyzing within this section. We're going to handle those things separately. First, though, let's go back to what I said close to the beginning of the video, where we're going to talk about what is a rational function. All right, and I'm going to compare a rational function to rational numbers because the concept is the same. What we said was, in order for a number to be rational, it needs to be able to be written as a quotient of two integers. All right, you have to be able to write it in the form p over q, where p and q are elements of the integer set. You remember that little q means integers? So a number like 3/4, for example, is a rational number because it can be written as a quotient of two integers. And there's several other numbers. You don't need me to tell you really what rational numbers are. You kind of have an idea of that already. Well, rational functions, like rational numbers, are functions that can be written as quotients. When we're writing a rational function, though, what we're going to do is we're going to write it in the form y equals p over x, p of x over q of x. And p and q both have to be polynomials themselves. So rational numbers have to be able to be written as ratios of integers. Rational functions have to be able to be written as ratios of polynomial functions. Now, polynomial functions can come in a lot of different forms, but here's a couple examples of some rational functions. A reciprocal function happens to be an example. This is a constant function, which is a polynomial, divided by a linear function. Or you could have this. This would be an example of a quadratic function divided by a cubic function. Those are each polynomial functions, and as a ratio, they make up a rational function. What we're going to be focusing more on are the reciprocal functions, though, and a rational function where it's the ratio of two linear functions, such as y equals negative 7x minus 6 over 9x plus 1, something like that. That's what a rational function looks like. Now we need to talk about the two separate forms that we mentioned in the beginning, right here and right there, that we're going to have to be sketching and analyzing. So let's do that. Let's look first at the rational functions that are in the form y equals k over x minus b, which are really just translations of reciprocal functions. And in fact, that's the first thing I want you to note about this. It is just a horizontal translation of a reciprocal function by the amount b units to either side. Now, since this is just a horizontal translation of a reciprocal function, we can just rehash some of the things that we already talked about with reciprocal functions and apply them to these y equals k over x minus b functions, such as what the asymptotes are. Now, the vertical asymptote is actually the thing that changes whenever you have this horizontal translation of a reciprocal function, because this little portion right here, x minus b, isn't going to be equal to 0 just because x is equal to 0. Now, I think you could agree with me that x is not allowed to be equal to b for this kind of function, because if it is, you would have b minus b is 0 and k divided by 0 would be undefined. So, since you're not allowed to have your value of x, your input value, be equal to this value b, that means that the value of b is your vertical asymptote. X equals b is a vertical asymptote. Alright, so then we're going to get right into where is the horizontal asymptote. And the horizontal asymptote, it turns out, is going to become kind of the same thing that we had with just the reciprocal functions, because there's no vertical translation happening here. Just as we said with reciprocal functions, it's impossible for any constant non-zero number divided by anything to give you 0. And so it's impossible for the output of this function to be 0. Just so you know, k is not allowed to equal 0, otherwise you wouldn't have a rational function in the first place. Alright? So if we divide a non-zero number by anything, we can't get 0, meaning that y equals 0 is the horizontal asymptote of the graph. Now there's one additional thing I'm going to ask you to do with these y equals k over x minus b functions as opposed to the reciprocal functions, and that's going to be that I'm going to ask you to state the domain and range. Something we could have done with those that we are going to do with these. Now remember, the domain of a function is the set of all input values that you're allowed to use for the function. And remember that there was only one value that we weren't allowed to use as an input for this function, and that was x is equal to b, because that's what would make us divide by 0 and get an undefined expression. So the domain of a y equals k over x minus b function is going to be that x is an element of the real numbers, meaning it can be anything except x cannot be equal to b. So x is an element of the real numbers, and it cannot equal to b. That's the domain. So you might write something like x is an element of the reals, but x cannot equal 5 if this happened to be an x minus 5. Okay, and the range is the set of all possible output values that you can get for a function. And that's kind of tied to our horizontal asymptote here. We said that we could get anything at all as an output value, any positive number, any negative number. It's just impossible to get 0 as an output value. So your range would be that y is an element of the real numbers, but y cannot be equal to 0. Now the graph is still going to be a hyperbola. That can't be said about the graph of every rational function, but all the rational functions that you're expected to know give you hyperbolas for their graphs. So, there. We'll keep coming back to that. Now I need you to actually be able to sketch a graph of a hyperbola and be able to identify the asymptotes and this domain and range of the function that gives you that hyperbola as well. So we're gonna do that with this example. We're gonna let f of x equal negative 5 over x plus 2. And so if we were thinking about what the k and the b are equal to in this function, we would have that k is equal to negative 5 and b is equal to negative 2. Right? That's the value that would make that denominator equal to 0. And so already we have enough information. Really, we didn't need this part right here. We have enough information to be able to determine where the vertical and the horizontal asymptotes are. Fill those in actually right now and see if you can state the domain and range as well based on the notes you've already taken from this video so far. You should have written that x equals negative 2, the value of b, is your vertical asymptote, and y equals 0 is a horizontal asymptote. Then for the domain, well, that's the x can be anything except for b, basically. So x can be anything, any real number except for negative 2. And then for your range, y can be anything except for 0, right? Alright, now on to sketching the graph of this kind of function. We're going to do this using a table of values, the same way that we did with just normal reciprocal functions that weren't translated in the previous section. So make a table of values. We're going to choose 3 points per branch. Remember, there's 2 branches for these hyperbolas. It's just that our middle number isn't going to be 0 this time, or rather the number that we can't plug in is not 0. We can't plug in negative 2. And so what I would like is to pick 3 numbers that are less than negative 2 and 3 numbers that are greater than negative 2. Now you can use your calculator to help you actually find the value of the ratio. You don't necessarily have to pick nice numbers here, but if you can pick things that would make you divide -5 by easy numbers, by like -1, -5, and so forth, that'd be nice. You're going to see the numbers I choose will kind of work out that way. So if I plug in -7, I'll be dividing by -5, which is easy. If I plug in -4, I'll be divided by -2, which is really easy. And if I plug in -3, I'll be dividing by -1, which is really easy. And I'll do a similar thing with numbers that are bigger than -2. Remember, the only requirement is this: x cannot be equal to -2. For whatever values of x you chose to plug in, go ahead and either evaluate them mentally or use your calculator to get an idea of what the y-coordinates are supposed to be. And then go ahead and plot those points and graph your asymptotes as well, so you can finish graphing the function. And if you're doing this on a calculator, make sure that you put the x plus 2 part in parentheses every time. There are my y-coordinates. Now I'm going to graph the vertical asymptote, which was the line x equals -2, and the horizontal asymptote happens to be the x-axis, so I don't actually need to graph anything for that. Alright, there's that line x equals -2. Now if you need to change your intervals on either the horizontal, vertical axis, or both, feel free to do so. Ones are sufficient for me to be able to graph all these ordered pairs that I've got. So I'm going to go ahead and graph those. And remember, then your boundaries are this line and the x-axis for your two branches of your hyperbola. So here's branch 1. And here is branch 2. Okay, so that's graphing basically a translation of a reciprocal function. I'm going to stop this video here so it's at a reasonable length, and I'll show you how to graph the y equals ax plus b over cx plus d in the next video. Alright, again, as always, thanks for watching, guys. Appreciate it. Let's do it well the next time, too.